We use implicit differentiation whenever we get a function that we cannot write in explicit form. That is a function that we cannot solve for y explicitly without getting these weird pluses and minuses, you know. So in this case, well, we treated the problem like an equation and take the derivative of both sides of the equation. Well, so before doing it the Calc 3 way, we're going to go back to the Calc 1 way, and actually you will find out how the Calc 3 way is just a lot better than the Calc 1 way. You'll see. Well, so let's take the derivative of this implicit function, find dy dx. And well, so take the derivative of x squared, so that's a 2x plus 3 times, notice in this case we have the product between x and y. So again, we're going to use our product rule. Let me write it down again. So that's uv prime, that's u prime v plus v prime u. Well, in other words, we differentiate the first factor, that's the derivative of x, which is 1 times y, plus the derivative of the second factor, y. But remember, from implicit differentiation, whenever we differentiate a y, we just write dy dx. And then, so that's a times the x, times x. And then minus the derivative of 5y squared. Well, we treat it like it's an x. The derivative of 5y squared is a negative 10 y. But in this case, because we're differentiating a y, we multiply by dy dx. Ultimately, this is like a mini chain rule to differentiate the y. And then equal to the derivative of 10, which is just a constant, that should be equal to 0. All right. So number one, let's clear parentheses and all this multiplication sign. So 2x plus 3y plus 3x dy dx. So this last couple of terms, we got them by distributing. And 1 times 3 is simply 3, and 3x dy dx. And well, minus 10y dy dx, and that equals to 0. So the way we went about implicit differentiation back in Calculus 1, so after we take the derivatives here, well, we're essentially done with the calculus, by the way. So the next step was to treat this problem like an equation and leave all the terms containing the dy dx on the left-hand side of the equation, and everything else just move it to the right-hand side of the equation. So let's then keep the derivative terms, 3x dy dx minus 10y dy dx equals to negative 2x minus 3y. And then, well, the idea of having all the derivative terms on the left-hand side is to make the dy dx symbol a greatest common factor. And then just divide out that 3x minus 10y. So this should give us dy dx.
Shouldn't it equal 10?
Equal 10?
Where you put equal 0?
This one? Yeah, but the derivative of 0, which is a constant, it's 0. So dy dx is going to be negative 2x minus 3y divided by 3x minus 10y. Well, actually, I would do one more step. How about factor out that negative in the numerator? So that's negative 2x plus 3y divided by 3x minus 10y. So, well, you might remember this kind of problem was a little painful back in Calculus 1. You know, all the steps, especially the tricky part when it came to differentiate the y's. It was very easy to forget to multiply by dy dx. So, in Calc 3, we're going to come up with a new way to find this implicit differentiation. So, okay. And in this case, we're going to do this by means of using the chain rule. Well, again, from the first page, we got this formula. Well, whenever we have a function z, which is f of x and x depending on t and y also depending on t. Well, let me actually use a different color. That's the dark. And okay. We got this formula from before. We got that the partial of z with respect x times dx dt plus partial z with respect y times dy dt. Well, so that's what we got from the first page, the general chain rule for two intermediate variables, but only one independent variable. So we're going to use this setting to come up with a new rule to find implicit differentiation using, well, you'll see. Alright, so this function f of xy is a function z. So the trick here is to make that function, whatever function, equal to 0. That is, whatever function we're given, define a new big F, send everything to one side, and that's going to create a new function. And well, of course, the idea is that y equals f of x, it's a differentiable function, and all that. So we're going to use, in this case, the chain rule. So in this setting, z equals f of x, y, in this case z minus f of x, y equals to 0, and in this case this will be our, let's call it big f of x, y. That's a new function, alright? So that's how we're going from little f to big F, not by integrating, so just so we're not doing integration ultimately. So let's change some notation. So we're going to find the derivative of the big F function, the new function we just created, with respect x. Alright, so these instances right here, these z's right here are going to become f and in this case we are no longer differentiating with respect t. So check this out. So we will be differentiating with respect x. So I'm highlighting this so you can see what I'm going to change over here. But essentially it's going to be the same formula with just new letters based on the new definition of the new function we came up with. So this will be times dx over, well, dt will become dx plus partial, no longer z, that's big F, over dy, partial y, and that's times dy dx. And in this case, notice this is equal to 0 because we're setting this new function equal to 0. But this should be also true that it's equal to 0 because, well, if this big function, this new function that we are defining, equals to 0, if we take the derivative of that function, well, what's the derivative of 0? So that's why that makes sense, right? To write this equal to 0 because this derivation is on the textbook, I think, and I don't think it explains why do we just set it equal to 0. So if you really like, well, why, you know? So that's the reason.
The plus sign is that dx dx.
Yes, dx dx. So in this case, well, What's dx? Dx, isn't it just 1? I mean, it's the same symbol, we're dividing the same symbol. And, well, so from here we get that, okay, I'm going to continue here. So df, well actually, I'm going to focus on this side. So partial f with respect x times 1 plus partial f with respect to y times dy dx. But isn't it that we are finding a formula for dy dx? That's our ultimate goal, right? So number 1, I'm going to subtract partial f with respect to x on both sides. And that's going to give us partial f with respect y dy dx equals to negative partial f with respect x. And then we're only one step away to get dy dx. All we need is to divide both sides by partial f with respect to y. So dy dx equals negative partial f over, well, with respect x divided by the partial f with respect y. And this is the formula that we were looking for in this case. In fact, this is the same formula that you will see in the definition box below. All right? So that's where the implicit differentiation formula is coming from, and by using the general chain rule for two intermediate variables, one and one independent variable. Well, even though yes, we're dealing with partial derivatives and the derivation looked a little crazy, well, actually applying the formula is going to be a lot shorter than what we did before the calc one way. So let's look at the same example. In this case, we have f of xy equals x squared plus 3xy minus 5y squared minus 10. Find the implicit, the derivative dy dx using the chain rule. Well, using the chain rule is really because we got this from the chain rule ultimately. So all we have to do is, number 1, find the partial derivative of the function with respect to x, which in this case is 2x plus 3y, and the partial derivative of f with respect to y equals okay, the derivative is 0 right here. Over here is 3x and minus 10y. Alright, so using this information, dy dx equals negative the partial of f with respect x divided by the partial of f with respect y. And let's just write what we have where it corresponds. So negative 2x plus 3y over 3x minus 10y. Yeah. Isn't it the same result? Yeah. Yes, I mean, we're using calc 3 methods, calc 3 techniques. That sounds like, oh, that's going to be more complicated. But no, in fact, it's making things easier. Don't we wish we knew this back in calc 1? Yeah. But well, there's an issue with knowing this in calc 1. We would have needed to go through partial derivatives, limits into variables, you know, but it would have been weird to talk about partial derivatives in calculus 1. And here, basically, in a couple of blinks of our eyes, right? Instead of going through the equation way, the painful way, you know. Well, these last couple of pages, well, let's add more variables to this. So we're going to have a function big F. This function big F is a function of x, y, and z. And each of these, x, y, and z, are functions of s and t, which are also functions of u, v, and w. Alright? Number 1, write f as a composition function. You know, what do I mean by a composition function? You know, like in a generic way, you might remember f evaluated at g, f of g of x. You know, that's one of the simplest composition functions. And in this case, well, it's a composition function in one single variable. But in this case, what do we have? We have two tiers of intermediate variables and finally one defining the independent variable. So let's start with the outermost. Oh, how about we do this? Let's fill in this diagram. Let's call this F. How about F? So F depends on X, Y, and Z. All right? Which at the same time, both X, Y, and Z depend on S and T. S and T. S and T. All right? And at the same time, each S and T depend on U, V, and W. U, V, W. U, V, W. U, V, W. Oops, that's W. U, V, W. And a couple more times. So of course, whenever you have a problem like this, even if you're not asked to do a tree diagram, just go for it. Just do it. It's gonna help us a lot. Well, so let's write the composition function again like f of g of x, but in this case with all these variables. So number one, this big F depends on x, which at the same time depends on s, which at the same time depends on U, V, W. All right? And then the next one, X, so that's not yet. Depends on S and T, which both depend on U, V, W. Comma, X, that's Y, which also depend on S and T, which depend on U, V, W. So that's Y of S of U, V, W, comma, T of U, V, W, and last but not least, we got the Z that depends on both S and T, but S depends on U, V, W, T depends on U, V, W. All right? So that's the given function using a composition function on how it's composed by its different layers, if you will, which each layer depends on, in this case, more than one variable. So let's see what's next. They're asking us to find a chain rule formula for the FDV. Okay, let me know when you're ready to get this one written down. So, find an expression, a formula for the partial of f with respect to v. All right, no, we're not going to do u, v, and w. We're going to do only one. That's enough. One is enough. All right, so let's explore all possibilities to get from f to v. And number one, let's go from f to x, x to s, and s to v. That's one. All right, let's write those down. So that's going to be partial f, okay, partial f with respect v. So number one, that's a partial f with respect x, and then partial x with respect s, and then partial s with respect v. All right? So far so good? Let's see if there's any other possibilities in this branch. Of course there is. Check this out. So we go from f to x again, but this time we're going to go from x to t, and then from t to V. All right? So let's write those partials. Partial f with respect x times partial x with respect, this time t, partial t with respect y. Oh, no, not y, v actually. Right? Alright, so we're done with those first two branches. Let's go to the middle ones. And let's see, let's explore the possibilities to go from f to v. So we can go from f to y, y to s, and s to v. So partial f with respect to y, partial f with respect to y times partial y with respect s times partial s with respect v, plus, what's the next one? The next possibility to go from f to y again, but this time instead of going from y to s, we go from y to t and then from t to v. So partial f with respect y plus, times rather, partial y with respect t, partial t with respect v. So we got 4 out of the 6 terms. So we're done with the middle branches. Let's go with the rightmost branches here. So f to c, z to s, and s to v. Let's go ahead and write that pattern of partial derivatives. Partial f with respect z, partial z with respect s, partial s with respect volume. And the last one, finally, we can go from f to z, but this time from z to t and t to v. All right, so let's go ahead and write this down. Partial f with respect z, partial z with respect t, partial t with respect v. All right. Pretty interesting chain rule formula, right? Well, the reason why I go something this crazy is because some of you are going to go through something like electrical circuits or network analysis. So, well, you may not use, or you may use this kind of network system to maybe find derivatives or some other type of calculation. So you'll see this later when you get into your engineering courses and the like. Alright, so let's do the last topic for this section. And well, actually this is not an official topic I'm supposed to cover, but the reason why I like to do this is because most, if not all of you, are set to take a thermodynamics course, regardless of your engineering course, or your engineering major that you are, electrical, civil, etc. I have friends who have taken this thermodynamics course. It's not physical chemistry. It's a little bit of physical chemistry. So, well, Anna, you're going to take physical chemistry. Any other chemistry majors here? Okay, you're a chemistry major, so most likely you're going to see this in physical chemistry in the thermodynamics area. Well, so this is called the triple product rule, also known as cyclic chain rule, cyclic relation, cyclic rule, or Euler's chain rule. And well, so this is the formula that relates the partial derivatives of 3 interdependent variables. So, and well, in this case, what we do is write each of the variables as an implicit function of the other two variables. And then in general, we're going to use this again in thermodynamics, in which we have systems of basically three variables: pressure, temperature, and volume. So what we're going to do here is we're going to verify this rule for the ideal gas law. So we're going to show that the product between the partial of the pressure with respect temperature times the partial of the temperature with respect the volume times the partial of the volume with respect pressure equals to -1. So let's see. So let's go ahead and write this Pva and Rt formula. And number one, let's solve for P. So that's P equals nRT over V. On the other hand, so this is what we're doing. We're writing one of the variables as an implicit function of the other variables, or as a function of the other variables T and V. And we're also writing the temperature as PV over nR. And last but not least, volume equals nRT over P and with the pressure. So this is what we're going to do. We're going to find the partial of the pressure with respect to temperature. So, well, in this case, the derivative of T, isn't that just 1? And everything else is just multiple constant. That's just nR over V. And then we're going to have the partial of the temperature with respect the volume equals so, well, again, here the derivative of V is just 1 times this multiple constant. That's just, we're just going to be left with a multiple constant nR. And the same time, okay, to differentiate the volume with respect to pressure, well, we need to rewrite this formula in a way that we can differentiate with respect to P, because we have it in the denominator, we cannot differentiate it there. And partial V with respect P equals negative nRT and P to the -2, which is nR, negative nRT over P squared. All right. All we're going to do is substitute where it corresponds in the cyclic rule. That is, partial P with respect T times partial T with respect V times partial V with respect P equals to -1. So we're going to put all this together and something pretty cool is going to happen here. So that's nR over V, that's the first factor, times P over nR times negative nRT over P squared. That should be equals to -1. And of course, check this out, a lot of common factors cancel out. So we can cancel this nR with this nR. We can also cancel one power of P with another power of P here. And I believe that's about it. So that's negative nRT over 1 power of P times the power of V that we got from the first factor. Is it true that this is equal to -1? Okay, let's go back to PV and RT again. PV equals nRT. Well, so if we divide both sides by nRT, we should get PV over nRT equals 1. All right? If we multiply both sides by -1, oh, check this out, it's true. That cyclic rule is true then, because then from here, -1, of course, is -1. All right? So this cyclic rule, which is in general something in mathematics, this is also applicable in thermodynamics. Well, in this case, it's a basic formula from chemistry, but of course, you're not going to use it with the real gas law, the van der Waals equation, which is a more elaborate situation than just the ideal gas. All right.